All right. 6.2. Bisectors of triangles. Day 2. Now, I just looked at what I had for my notes. I audibly did Peter Griffin. Holy crap. Because this is one page. We definitely could have done this yesterday, but no, I don't want to do it. Oops. So, today is going to be the other half of 6.2. It's going to be quick. In our case, we are going to be learning a new thing. And you see, look at here, the Insetter theorem. Ooh. Really taking this slow. I really don't want to start a 7th unit, if you can't tell. So I'm rambling. Anyways, let's get started so we can be done. If you hear any noise, it's my dog's birthday right now. We just celebrated. He got a new toy. I bought him a squid toy today. And I'm so off task. All right. Just as a triangle has 3 perpendicular bisectors through each side, it also has 3 angle bisectors. Yeah, 3 angle bisectors, 1 going through each angle. I did not have a comma where I should have, so that's why there was a big pause. All right. So with all the perpendicular bisectors that we have, there's also going to be 3 angle bisectors that we have going through the triangle. This goes into the theorem we're about to go into. But the angle bisectors of a triangle are also congruent. This point, not congruent, are also concurrent. This point of concurrency is I'm going to use a different color for this. Incenter of the triangle. Which always lies inside of the triangle. So we wouldn't have like any fancy dancy perpendicular fancy dancy point P's anywhere, like not on the side or outside of the triangle. It will always be inside. In center, always inside. I'm gonna write that down in red. You need to know this. In center. Oh no, my red is running out. In center. Oh my god. Always inside. There we go. Always inside triangle. There we go. Better. This helps us with the in-center theorem, which states that the in-center of a triangle is equidistant from the sides of a triangle. So that means, did I use the right picture? I in fact did not use the right picture, I think, for this one. Oh god. No, I didn't use the right picture. You gotta be kidding me. This is I'm raging right now. Oh my god. Oh my god, Monty. Alright. Oh crap. I'm about to crash out. Oh my god. Alright. Oh, there's a squid. I hear it. It's squeaking. Alright. Let's what do I do? I'm drawing a new one. This video gets a new one. if you're watching, if you're in class right now, I hopefully figured something else out for the in-center. All right. I'm trying to just copy it to what I best have in my notes right now. Bear with me. And making the picture larger so you can see it a tiny bit better. So we have this happening in our picture right now. Oh, this is rough. So I want to write an if-then statement to kind of help understand what I'm trying to think of. So if PA, PB, and PC are angle bisectors, so if we have angles like this, so remember angle bisectors, congruent angles, all that stuff. If this is happening, oh, I don't like that green. We need a darker green. Then PD is equal to PE, which is also equal to PF. Also, these are perpendicular. That's what that theorem is stating. On triangle ABC. So if we have angle bisectors coming out from A, B, and C, then that means that PF, PE, and PD will be the same length. They will be the same bisector. Bisector, oh wait, well, in-center is not the same as circumcenter. Not the same. They are not the same. Unless if you're an equilateral triangle, then I'm pretty sure they're the same. But no, they're not the same. In-center, circumcenter, not the same. They are not the same. Not the same. So remember that. But we have problems that we can work with. Example 1. This is going to be easy. I'm going to have to drag out the actual class time for this. All right, let ND equal 5x minus 1 and NE equal 2x plus 11, and we got to find NF. So looking at my figure right here, I see some angle bisectors, and all 3 of them have angle bisectors. So guess what that means? NF is congruent to ND, which is congruent to NE. So that means I can set ND equal to NE because they're congruent and find out what X is. X minus 1 equal 2x plus 11. Got to get X all by itself. So 3x minus 1 equals 11 plus 1 over. We get 3x equals 12. Divide by 3. X will equal 4. Why am I trying to find X right now? Well, I'm going to plug it into one of these 2 values. Once I plug it into one of these 2 values, then I'll be able to find out what NF is. Because, you know, NF is congruent to ND, which is congruent to NE. So they all have the same value. So if I know the value of one of them, I know the value for all of them. I'll pick ND. ND equals 5x minus 1. So that means I have 5 times 4 minus 1. So 20 minus 1 equals 19 for ND, which is also NF. So I got 19. Not too bad, is it? I think it's not too bad. I think you guys are okay. You better use today as a work day. Or use Thursday as a work day. Oh my gosh. If you're not caught up with any of this, please use today as a work day. You can tell I'm dragging out this unit so I don't do too much. If not, I'd have a full week of nothing to plan for. Like, oh God, that's horrible. Example 2, doing the same thing. We have angle bisectors on C, B, and A, so that means NF is congruent to ND, congruent to NE. ND equals NE, which is equal to NF. So that means I can set NE equal to NF to get ND. So ND is don't even write that. 6x plus 1 equals to 4x plus 15. Get 4x over to the other side to get 2x plus 1 equals 15. Minus 1 will give me a 2x equals 14. Divide by 2, and we'll have an x equals 7. Remember, take this x, plug it into your favorite one, either NE or NF, to get ND, because they're all the same value. On the inside, so I'll pick NE, so 6 times 7 plus 1 equals NE. 6 times 7 is 42 plus 1 equals NE. And that means I end up with 43 equals NE, which is also ND, because they're all congruent to each other. Not too shabby. Now is it? Yeah, I don't have too much for this one. This isn't too bad. I will find a way to fill out time in class, I think. Yeah, I'll figure out something. Hopefully you enjoyed. If you're not done with any of this, please take the time to catch up today. I think that would be your best interest. There has been a revelation. This is combined with 6.2 day 2 because there's a snow day on Thursday. I'm unfortunately doing this on that snow day. I don't get the day off. And I'm also gone on Friday, so whoop-de-doo. So we get a double lesson. To be fair, it was only maybe 8 minutes worth of video that I actually did that was actually notes. The rest of that was probably more me complaining. Today, I am going to do the full lesson of 6.3. This is also the last lesson before the quiz that we have on Tuesday. Most likely Tuesday. I'm not going to change it until I see what you guys have done. You better do your homework. Anyways, let's get started. Median of a triangle. What is the median of a triangle? Well, it is a segment from get a different color. Vertex. Oh no. I'm wearing gray. Can't have that pen on me. Ew. I don't want ink on me. Vertex 2, the midpoint. Of the opposite side. What does this look like? Well, we get to draw it out. Ooh-wee, baby. So, let's take B, for example. The median of the triangle will be kind of just a line going down. It doesn't have to be perpendicular, but that median is going to create it will create, all right, this median, this line that's created does not have to be perpendicular, but this line that is made, this DB, is kind of splitting this AC in half. That's what the median of this triangle does. It goes from vertex B, which is not above D, which is our midpoint, but that's the line. That's what the median of a triangle is. So when three medians of a triangle are are concurrent, so they all cross, have an intersection, this point of concurrency, that point of intersection, is called the centroid. And we have a centroid theorem to go along with it. So what is the centroid theorem? It's the intersection of all these medians. So the centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. So looking at our figure right here, good. There's a takeaway that we can have from this little figure that we have, and it's going to be an equation that we'll be using in this example down here. So take notice of like where this intersection is right here and what happens. Let's take this segment AE and P, for example. So what this centroid theorem is telling us, and it's working with the lengths of all the lines on the inside of this triangle. What this theorem is telling us is that, let's just say, for example, we're going to look at AP, the segment AP. I'll get my orange colored pencil to color that in. I'm going to look at AP, that segment. AP does have something that's equal to it. AP is equal to 2/3 of the whole segment of AE. All right, to take note, theorem tells us long part is equal to 2/3 of the full line. There you go. Seeing this in practice makes a lot more sense, but that's what our theorem is telling us. The long part is equal to 2/3 of the full segment. So looking at example 1 on like how to actually do this, my slipper is off. My feet are cold. We have triangle RST, and point Q is the centroid, and SQ is equal to 8. And we need to find QW and SW. So SW, I guess we should label stuff out. That might help us figure out like what the heck everything is. Looking at our figure, also remember, I write out my thinking. Do the math. You just need to show me the math. You don't have to write out what I think. I write out my thinking so that you guys can kind of see where I'm getting everything from. You don't have to write out my thinking in your actual homework. Just give me the math. If I tell you to write your thinking, then you better write it. But I'm not asking you to write your thinking for this. So looking at our figure, but I want you to put in your notes just in case. But unlike homework, you don't need to. Looking at what we have, we can see that SW is the full line. SQ is the long part. And QW is the short part. I can find my answer at this point for everything. Because first off, I can find QW. Well, first, how about let's start off with doing SW, because that's easier, because we can use this up here. I'm going to circle this, because this is the main takeaway of the theorem. That's our takeaway. That's our, like, put together equation for this problem. So if I were to start building that equation, I have the long part, which is SQ. So I have SQ is equal to 2/3 of the full line, which is SW. Now let's fill in what I know already. So SQ, oh wait, no, that works. There we go. We didn't have to scribble out because SQ does equal 8. And we can't fill in anything for SW, so it stays the same. But now I can find SW, because I can just do 3/2, because that cancels out that side. Now I can do 3 times 8, which is 24, divided by 2, which is 12, equal to SW. So I'm going to put 12 up here for my answer. And now I can find QW so much easier. Now we don't have an equation to find QW at all. Uh-oh. What am I gonna do? So I think what I'll do is kind of just write it out as like SW plus, nope, SW equals SQ plus QW. You know, the big segment equals the little plus little segment. Fill in what you know. I have 12 for SW, I have 8 for SQ, and then I don't have anything for QW. Look at here. I can get QW all by itself and get a value. Subtracting 8, I end up with 4 equal to QW. And there we go. That's my answers. QW is 4, SW is 12. Using this equation that we built. I think I explained, hopefully I cut that part out. I hope I did. That'd make everything a lot more nicer if I cut that part out. But this is the main takeaway. As long as you know this, problems like that, not scary. You're able to find anything you want. You will have to be asked to find the centroid of a problem as well. Maybe in the grid formation that we have seen before. Ha ha ha. So in our example, we're going to find the coordinates for the centroid RST with the vertices of RS and T right there. Step 1. There's 3 steps. Step 1. What do you think it is? Guess. We're going to graph. You have to graph it. It'd be hard to find the centroid without graphing this one. I'm going to be honest. So I would highly recommend graphing. So 2 over up 1, that's R. So we got to go 5 over. So 3, 4, 5, then up 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's S. Then T, it's 8. 6, 7, 8. Up 3, 1, 2, 3. I almost put it at 2. Maybe a T. I don't like working with graphs. I can already hear the comments of like, oh, then why do you make us do graphs? Because I want you to. Step number 2. We need to find the midpoint of the sides. What? Yeah, okay. Yep, find the midpoint. Of one side. Let it be an easy side. Remember our easy sides are horizontal lines and vertical lines. Find your midpoint on one of those. Ooh. Just kidding. So we need to find the midpoint on easy side. Easy for counting. You'll see why in a second. Because we got to count for our centroid. You'll see why. So I'm going to pick RT to be my midpoint. Or I want the midpoint of RT. So I need to do 2 plus 8 over 2 and 1 plus 3 over 2. That'll give me 10 over 2 and 4 over 2, giving me, I'm running out of room, 5, 2 being my midpoint. And I'm going to plot it right here. And that's 5, 2, all right. I want to name it V to be my midpoint. Why do I say let it be an easy side, easy for counting? Well, because we're about to count for our centroid. So let's do, I gotta write step 3 now, because this is going to be finding the actual centroid. Step 3. Find the centroid. I have no idea if I'm saying that right, by the way. All right. Why do I need to pick a point that's easy for counting? Well, look here. If I had to... This is so easy to count. Because one, I have to count to one of the vertices up here. And to make it easier for counting, you got to be on a vertical or horizontal line. Look at here. This line from V to S matches up on my grid. So it's the easiest one to count, which is why I picked RT. So RT is the easiest segment to count with, which is why I picked it. That's how you should pick your midpoint, or how to find it, which is why it's important to graph, and it makes counting a lot easier because we can see that we go up 1, 2, 3, 4, 5, 6 units. Woo. And remember, the centroid and how we graphed it, it was broken up into 2 segments. We had the long part and then the short part. And the long part was always 2/3 of the total length. So that means I need to go 4 units. So go 1, 2, 3, 4 units. Go right here. It's 4. And this point right here is going to be my centroid, which is what? 5. 1, 2, 3. 1, 2, 3, 4. 5, 4. That's my centroid. This is why it's the easiest one to pick. Because I can count straight up and down. It makes it so much easier. Yeah. Nothing too much to say for that one. I think that one's okay. I think you'll be okay with this one. Last thing to do is to learn about altitude. Now, yep, we're going to learn about altitude. So what's an altitude, you might be asking? Well, an altitude of a triangle is the perpendicular segment from a vertex to the opposite side, or to the line that contains the opposite side. So basically what the altitude is, it's telling us the true height of the triangle. Good to know. I would make a note. Make a note. Say that this tells the true height of a triangle. Cool. The line containing the altitudes of a triangle are concurrent, and this point of concurrency has a special name called the orthocenter. And yeah, that's it. So when these all cross, all the altitudes cross, they make the orthocenter. And just kind of like circumcenters, these also have different places in triangles. More specifically, it's different in acute right triangles and obtuse triangles. So for acute triangles, always inside. The orthocenter is always inside the triangle. For right triangles, it's always on a side. And for obtuse triangles, It's always outside. I spelled outside wrong. You'll need to know where the orthocenter is on each one of these. But it's also the same kind of remembering that you have to do for circumcenter. So not too bad. Cool. That does not mean the orthocenter and the circumcenter are the same point, but they have the same property on where they could be in a triangle. One last thing that we're going to do today is kind of fill out a chart of the centers that we have kind of found recently. So I have a grid that we will be filling in because we are on the grid. And we'll just start filling it out. Like the first one that we have in this box is the perpendicular bisector. It looks like this. We get the perpendicular line with the right angle box making these two segments congruent. The perpendicular bisector goes through the midpoint. And the point of concurrency for a perpendicular bisector, which is called the circumcenter. And the circumcenter P of a triangle is equidistant from the vertices of the triangle itself. So if we have circumcenter P, it makes PA, PB, and PC all congruent. This was in 6.1 day 1. Next one is the angle bisector. When we have an angle bisector, it is a line, ray, or segment that cuts through one of our vertices, creating two perfectly congruent angles. And when all of these lines cross each other, they are called, well, that point of concurrency is called the incenter. And the incenter I, in our case, we're going to label it as I, of a triangle is equidistant from the sides of the triangle itself. So if we have angle bisectors, that their intersection will create all of these perpendicular bisector lengths congruent. They're all the same length. And this was in 6.1 day 2. For this one, was it 6.1 day 2? No, this was 6.2 day 1 and 6.2 day 2. Incenter is what you did today. My mind is going crazy. This one is the median. Yeah, okay. I was like, am I writing this right? So the median, it is a line that's formed from the vertex that goes to the midpoint. It does not need to be perpendicular, but since it goes to the midpoint, we have two congruent spots right here. The center of this is called the centroid, or the intersection point of all the medians is called the centroid. And the centroid R of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. So that means if I have, let's just say, CR, let's call this point E. If I have CE equal, let's say, 9, that means we have the segment CR and RE. CR is going to be 6 and RE is going to be 3. That's what the lengths would be on this segment going through here on that one. And then our last one that we have is altitude. And what an altitude is, it is just going from the vertex straight down to one of the opposite sides or a line that contains the opposite side. It gives the true height of a triangle. And when all the altitudes intersect, it creates the point of concurrency called the orthocenter. And the lines containing the altitudes of a triangle are concurrent at the orthocenter right here, and we have 3 different ways the orthocenter can be shown. That's all for this packet. We will have our quiz on Tuesday. I will gauge how we are feeling on this stuff on Monday. You guys better do the homework. I will be very disappointed if you don't. But please do the homework. You have the time in class. And I will see you guys on Monday.